welcome everybody. This is the breakout session on reducing complexity and generating valuable new insights from IoT data. We have a great set of panelists here that cover a range of areas, including healthcare, smart energy, and IoT analytics platforms. I will start by talking a little bit about smart grid to give you some context for our subsequent Q&A session. And then each of the panelists will speak briefly as well about their respective areas. Oh, well, this was the wrong button. So let me start out by talking briefly about the first major area where IoT analytics plays an important role. And that is for improving grid operation. In particular, one of the major challenges facing grid operators is balancing the supply and demand of electricity. In the absence of grid-scale storage, which is currently not feasible, we have to forecast the demand for energy, or the load, and in order to produce just enough to meet that demand. And this is an illustration of the traditional architecture of the grid, if you will. It's a very simplified illustration. We have generation facilities which produce power, and then the electricity gets delivered to the end customer over the transmission and distribution infrastructure. In the past, we only had a very rough idea on a monthly granularity or so about what individual users were using. But with the introduction of a very well-known IoT device, the smart meter, we now have interval data which has granularity of 15 to 30 minutes, where we know the usage of each user at this very high level of granularity. Smart meters have bidirectional connectivity to the utility, so we can get a lot of other interesting information, especially since advanced metering infrastructure networks, the networks formed by smart meters, also are on occasion used as backhaul networks for other types of data from, for example, distribution system devices. We talked about how forecasting of demand is an important problem due to the introduction of renewable energy sources such as solar and wind, which are variable and also not in our control. Forecasting of generation has also become an important problem and also requires collection of data and analytics over that data. We're already seeing a little bit from this presentation that the grid is becoming increasingly more complex. And with more sophistication and complexity comes a higher risk of faults. And just as if we do not balance supply and demand properly, we can get blackouts. Faults cause blackouts, and blackouts are, of course, not only disruptive, but very expensive due to the universal reliance on technology that we experience already. Deploying measurement and control devices across the grid can help us identify precursor conditions for faults and avoid some of them, and the ones that we cannot avoid, we can, using analytics, find configurations of the grid such that we can isolate and localize the fault and maintain as efficient operation as possible. Finally, cyber security and physical security are major challenges that IoT analytics can help with. And these are problems not only because of, again, disruption of the operation of the grid and expense, but also because they can be a cause for national security concerns. And by, for example, providing information from across the grid, we can detect, using analytics, changes in behavior that might indicate an impending attack, which would otherwise be too subtle to detect with traditional means. And just very briefly, at FLA, we have several projects that touch on some of these areas. We've conducted research in load forecasting for commercial and industrial sites. And we also had a collaboration with several universities, UIUC and UT Dallas, on traffic analysis for intrusion detection systems for advanced metering infrastructure networks. And that work won a Best Paper Award at last year's Smart GridCom. A second major area that I wanted to touch on very briefly here, where IoT analytics plays a role, is energy efficiency. One way that we can improve the efficiency of the grid is by instrumenting appliances and devices and trying to understand when some of them are unnecessarily inefficient. In addition, we can track their behavior over time and figure out when they start to behave out of profile in a way that wastes more energy. And in addition to looking at devices, a way to try to improve efficiency is trying to also motivate people to be more efficient. And some first steps in this direction are to show people how much electricity they're using and also show them how much each of them. We can try to extract the usage of different devices within the home from the overall electricity usage of the home. So without instrumenting each appliance, based on the overall electricity usage, we can extract the different device loads. Another application that I wanted to mention here, which plays a role in supply and demand balancing as well, but I have it here because it involves the user, is demand response. And very briefly, demand response is a service whereby the utility company, at times of great demand or high electricity prices, can send signals to certain users to ask them to reduce their energy use temporarily. For example, when you get a signal, you can perhaps temporarily stop charging your car or reduce or increase the set point temperature of your air conditioner. And here at FLA, we have done some work on some of these topics as well, and we have a couple of demos in the back related to demand response, which hopefully you've all seen, but if not, I encourage you to do so. Another project that we have is on load disaggregation that I just described. We've also looked at demand response forecasting, participation forecasting, because yes, you can send the user a signal to reduce their usage, but they may not necessarily do so. They may be feeling lazy at the time, for example. So how can we predict who will respond to a demand response signal and how much electricity will they, how much their usage will be reduced? We've also started looking at gamification for DR. Again, how do we get the customer more engaged so that they, when they receive a signal from the utility to reduce their energy usage, they will in fact do so. And I have a couple of questions that I wanted to bring up here very quickly. I just touched on people's behavior. So how can we change people's behavior? Many people say that they want to be efficient, they care about the environment, but they don't actually do anything about it. How can we help them be more efficient? Also, there's a very fine balance between providing the user with too much information and providing the user with too little information. Users really like automation, but they also like to be in control. So how can we do both well? And in many application areas, it is difficult to provide automation yet because we don't understand the problem well enough. So we do need user feedback. How do we keep the user in the loop without irritating them? And the last question is, we have a lot of IoT devices and a lot of analytics that can benefit from sharing. So how can we do cross-application analytics to maximize reuse of both the devices and the data? Now I will introduce our next speaker. Ajay Chander is a research manager at Fujitsu Laboratories of America. And he will talk to us about human-centric IoT and services for healthcare and life in general.
So this is for me?
Yeah.
Okay, great, thank you. Thank you, Jorjeta. And good afternoon, everyone. I thought I would share briefly with you guys our vision in the lab at Fujitsu Labs of America of human-centric IoT and some of the work that we've been doing to bring that vision to reality. So we all know that with the passage of time, computers get more powerful, and the same computing capacity becomes available in smaller spaces. So in terms of our human visible interface to computing infrastructure, it makes sense that we have gone from mainframes to microcomputers to desktop computers to laptops to smartphones, and each of these things has taken about a decade. And now we are in a phase where computers are small enough that they're becoming embedded into things. So if you put a computer inside a weight scale, it can tell you, it can tweet your weight if you wanted to do that, but it can certainly track your weight. If you put a computer inside a wristwatch, it can tell you how active you've been and how well you've been sleeping. So we get a bunch of human sensing around computers embedded in objects on us or inside us. Taking that a little bit further, there's computers embedded inside things that we interact with on a daily basis. Take the toothbrush, for example. A computer or computing elements embedded inside a toothbrush or a much bigger thing like a car starts sensing our behavior around these everyday objects. And then finally, there is an element of environmental sensing. So we've got a power switch that is connected to the web or a personal weather sensor. So with computers becoming embedded in more and more of the analog world, what functionally IoT is doing for us is that it's making more and more of this analog world digitally readable, which makes it possible to build really new kinds of services. And for us in the lab, one of the most exciting things about the promise of this era of computing is its potential to transform entire service ecosystems, which currently are provisioning their services in manual and inefficient ways. So let's take healthcare as an example. We've looked at healthcare a bit, and the promise of IoT in this domain is high. At a very high level, you can think of healthcare as really trying to solve two basic questions. The question of how are you? What is your health? And the question of how can I help you be better? But the way that the system answers these questions today, and this has been the case for centuries, is in a very manual manner. Even the user or the patient has to manually take the initiative to bring themselves to a special place called a hospital, where there are special people called nurses and doctors that put special equipment on us to take all the data they get off and put it again in a special place that only they usually have had access to, the electronic medical record. And on the care side, the engagement with the system ends with a prescription or a piece of advice given to us, and it is left to us to follow on it as best as we can. So the entire system currently is very manual and episodic. On the other hand, an IoT-enabled healthcare system, you would use continuous sensors for continuous sensing to answer the first part of the question, how are you? And to know the answer to that question in places and contexts much broader than a doctor's office. And to answer the other questions, it would use continuous diagnostic measures and connect us continuously to the traditional providers so that we use them more efficiently. So this model of using continuous digital services to improve the efficiency of service ecosystems, to me, is one of the most exciting things about this era in computing. And I think truly we are able to serve an order of magnitude more users with a better quality of service for cheaper with where we are in the computing era. So at the lab, we have been looking at this problem for a few years. And in order to sort of usher in the era of personalized digital services, we started work a few years ago on a software platform that was specifically designed to make it easy to write services that leverage sense data that in particular comes from mobile sensors and is high velocity. So healthcare has a lot of examples of that kind of data. because it comes from our bodies, so the data is mobile, and for example, cardiac data is a high velocity data stream. We call this platform the Sprout, and it's available now as one download on practically any Android device. And although originally motivated by applications in healthcare, we designed it so that any IoT domain service can be written on it in a pretty modular manner, using an open API that allows somebody to choose their sensors of interest, choose or build their analytics of interest, or reuse sensors or analytics that other people have built. And one of the things that we also did in our lab, really as a way of sort of building the platform itself, was do some research on building a variety of stress algorithms that utilize data from mobile sensors. A lot of work in this field has only used data from static sensors in the lab. And stress is well recognized to be a very important element of day-to-day wellness as well as long-term clinical health. So now what I want to do is jump into a few examples of deploying the Sprout in the field and how it's been used with various partners, just to give you a flavor of how human-centric this IoT era really is. So I don't know how many of you are Formula One enthusiasts. I have to say I was not very aware of this field before we started working with this particular partner. But the drivers in these cars are truly athletes. They sort of maintain their bodies, maintain a training regimen just as much as an athlete in any of the more popular sports like football or baseball would. And they're really trying to perform at a very high level competitively. So in this example, in this deployment of an IoT service, what we did was we put a little sort of chest sensor. You can see that on the chest of the driver, which would measure in real time his EKG, from which we could compute on the platform in real time stress. Now, the car is moving around. It's got a GPS sensor on it as well, and that GPS sensor measures location. So because you have a platform, you get synchronization of data streams for free, and you end up being able to analyze and look at the data in many interesting ways. So over there, that sort of colored loop around the track is essentially each dot being a location of the driver on the loop, and the color of the dot is the stress that the driver felt at that point in the loop. So, and imagine how useful this information is to try and opt for the coaches, for the athletes themselves after the fact, to optimize themselves, especially for especially if they know where they're going to be competing. And then over there are some examples of how their stress changes when they approach or don't approach a lap. I'll point out this one. Let's see if there's a pointer here. Yeah. So this one, the red lines show pit stops. You know, you're going around a track many times. There are pit stops. And this pit stop is a planned pit stop. And the black line shows stress. So this is a planned pit stop, so the stress starts going down as you approach the planned pit stop. This is an unplanned pit stop. And see how the stress just goes right through the roof because something has gone wrong enough for the driver to decide, I need to make a pit stop. And having this lens into information that was so far invisible, how is this athlete reacting to an unplanned situation, is really what sort of coaching them is partly about. So the next example sort of goes to the other end of the spectrum. We're now not looking at optimizing human performance, but bringing human performance back to normal standards. So we worked with the National Center for PTSD at the VA hospital in Palo Alto, and they were running a program to rehabilitate veteran drivers for civilian driving conditions. There are 25% higher accident rates, at-fault accident rates, in veterans after return from active engagements than the normal population. And the reason is because the way they are trained to drive in war scenarios requires them to be paranoid, requires them to be aggressive, requires them to go through a red light if they see somebody suspicious waiting for them, requires them to look at objects by the side of the street as potentially life or death explosives. So it's one of the issues, one of the factors that PTSD leaves them with is a difficulty in unlearning this behavior. So the protocol that the National Center for PTSD came up with was to instrument a car very heavily, the steering wheel, all the pedals, the driver with a whole bunch of sensors, the location of the car itself, cameras on the mount, and so on and so forth. But they didn't have any way to get all these sensors to talk to each other because they really wanted to know when the heart rate spiked, where were we on the course? What happened to driving behavior and so on and so forth. So we worked with them to deploy our platform and enable all the synchronization of real-time signals so that in the end they could look at a panel like this, a gap in this. Each line there is one of those signals I talked about. The gap is an event happened. The driver got very anxious while driving around. And you could look at the data and try to figure out what actually is the real issue that we need to provide some therapy for this particular person. In addition, the real-time nature of the platform makes it possible to provide, in this case, a visualization of their own breathing signal as a method for relaxing when such an event has happened on the side of the road. And that just was part of the therapeutic protocol. So, and then the last example here is sort of in between the two extremes. This is all of us, you know. This is us at work every day. We have some stresses, we have some things that we're good at and trying to get better at. And this was something that we did with Sony Pictures to look at a subset of their population and to instrument them and to instrument their desks. Turned out in this study, what we were really trying to do is see what if you replace their regular desks with sit-to-stand desks. So what if your environment at work changed? And you can imagine it not being a sit-to-stand desk change. It could be a new kind of keyboard or a mouse or a new kind of chair. Each of these things, Internet of Things, each of these things can now be digitally readable. How much are you leaning back in your chair? How many times you're standing up and down? And you can derive some really impactful data-driven insights, which in the case of these folks drove them to make business decisions about how to invest for the wellness of their employees at work. So this is the last slide really to sum up on the note that for us, Internet of Things services certainly provide new business solutions, but they provide new business solutions in the way that the web provided new business solutions 15 years ago. The web, not eliminated, but transformed by orders of magnitude transaction time. And the Internet of Things is transforming by orders of magnitude decision-making time. And it will lead to just as big of a change in how services are deployed in businesses. And in this case, because the data involves us, there'll be a lot more personalized human-centric services that come out of this era. So I'll stop there, and thank you for your attention.
Thanks. And now I would like to introduce Naoki Akaboshi. Akaboshi-san is a director at Fujitsu Laboratories Limited, where he focuses on development of storage and database systems. He will talk about how IoT changes the way business is conducted and the reasons why ICT platforms need to be changed to meet the requirements of IoT. Thank you.
Thank you, Jorjeta. I'm Naoki from Fujitsu Laboratories, Japan. It's my pleasure to be here to discuss this interesting topic. And I have been developed the Fujitsu products such as database systems and storage systems. And today, I'd like to talk about IoT eras, innovative ICT platform a little bit. And first slide, we have a rapid data growth, especially in the unstructured data. And in this EMC research shows that the data is doubling in size in every 2 years. So in 2020, in the year of the Tokyo Olympic game, we will have 44 zettabytes of data, which is 10 times more than 2013. And the rapid increase, some of the reason are the number of the sensors are increasing. You are using the smartphones, and there are many sensors widely used, as Jorjeta and Ajay has already mentioned. So we will face more data in the future. And so this slide shows the digital in the data in the digital universe. But as Ajay told, that even the analog service can be digitalized. If you buy the real item in the Amazon, that transaction will be digitalized. So data will be increased in the future. And next slide. So, okay. We have huge number of data. And this data is driving the innovation. I will show you some examples. As Kiname-san has already talked about the Fujitsu Cloud Service Agriculture, Akisai, in the previous session. It heavily used in using the sensor data for cultivation scheduling. So Fujitsu has succeeded to harvest low potassium lettuce, which is known to be good for kidney disease. And it was also known to be very difficult in watering. So we use the sensor data to harvest the low potassium lettuce. And the next example is automated identification technology. And this is a Fujitsu's technology. And Airbus selected Fujitsu's RFID for the service and maintenance. This is a very primitive case. But in the future, these kinds of data can be taken from the sensors. So we will be able to maintenance and manage many kinds of data from the sensors. And next, and in this IoT era, the data can be useful for the enterprise. Enterprises can benefit from IoT data in many areas. However, significant challenges exist in using IoT data to drive value in the enterprise. One reason is expanding velocity, volume, and variety of data require new technology solutions because huge data and the network bandwidth is limited, so we need new technical solutions. And the second reason is retrieving useful information from the unstructured data is very difficult. And it needs a large computing power. Today, we have very fast computers, but still, we have a lot of time necessary to retrieve the information from the video images or the sensor data or the streaming data. So the computing ability, we need more in the future. And related to the second reason, the third reason is very, very important in the ICT area. And 50 years, number of transistors doubled in every 2 years. It's like the data increase. But this is called the Moore's law. But the Moore's law is slowly ending. And Moore, he himself told that in 10 to 20 years, we cannot make the transistor smaller. So the Moore's law is ending. So, but we still need a powerful computer. We still need a powerful computer for machine learnings and data minings and the analysis of IoT data. So there's the gap. We can provide we need to provide a faster ICT platform in the IoT era. And there are many challenges are going on. New architecture to accelerate the IoT data computing. One example is a GPGPU or the FPGA. As you already know, that Microsoft and China's Baidu has adopted the FPGA to accelerate the searching engine using the FPGA. They got the much faster searching engines. And another approach is neural networks. Some of you may know that in the 80s, a neural network was very, very popular. And it was a very hot research topics. But at that time, computing power was limited. So it did not become the mainstream of the computers. But right now, Moore's law is ending. We cannot speed up our processors maybe in 2 or 3 generations. So we need the different approach to process, retrieve the useful information. So the neural networks is one candidate. And even the neural chip is now researched in many research organizations. So this is the second approach. And the third approach is quantum computing. And some companies are already working on this. And these are very different approach, not just speeding up the CPU, but a different approach will be needed to retrieve the IoT data, useful information from the huge IoT data. So in the future, our ICT system will need to provide a new architecture which can handle the huge amount of IoT data. If the Moore's law will end, but the data will still increase. So we need to handle these IoT data in the future. So I'm very interested in this kind of new architecture for processing the huge amount of IoT data. So this is the end of my talk.
Thank you. And finally, I would like to introduce Kyle Wild. Kyle is the CEO of Keen.io, which is a Bay Area startup focusing on enabling developers to build customizable analytics platforms.
Hello. Is this thing on? Cool. I'm Kyle. So I didn't really prepare any slides, but that's great. I'm an improviser. I took some notes. I think I'm going to open with a story. How much time do I have? Several minutes, I'm told. That's code for it depends on how good the story is. So how many people here have heard of the name Tycho Brahe, or if you're Danish, Tycho Brahe? Pretty good, okay. Sciencey crowd then, usually that's like nobody. So for everybody else, I'll fill you in. So Tycho Brahe, which is how I like to pronounce it, was a 16th century Danish aristocrat and kind of a hobbyist astronomer. So he was an aristocrat, meaning he had a ton of money and a ton of time, and that's kind of what he did was astronomy on the side, and then it became kind of his obsession. So one of the things that he did in the 1500s was he built the greatest observatory that we think humans had ever built by that time. Maybe the Mayans had something, but it's just ruins. So we think he built the greatest observatory of the heavens that humans had ever built. And then he went out in his observatory every night and wrote down for every star and every light he could see in the sky, planet, whatever it was, he wrote down the position and the brightness. And he did that for 30 years, every single night. Took some time off for parties. He was a little bit of a partier, but mostly, almost every night. And then 30 years later, he died. But some people have heard of him, so you know that there's something else to the story, right, besides him dying. So luckily for all of us here, Tycho Brahe had an assistant whose name was Johannes Kepler. Johannes Kepler, I'm assuming most of you have heard of. So what Kepler did was he took the data, and he had this huge collection of notebooks with all of these positions and brightness, just the work of a total madman. But it was really, really specific and well done. I heard somebody from NASA recently call it history's most ambitious attempt at accuracy at a large scale. I think that's probably true before we had computers. Now we get to be more ambitious. So Kepler took the data, and he devised the laws of planetary motion that we use today. Without Brahe's crazy notebooks, humans probably wouldn't have already gotten to space and be sending probes to Mars, and maybe we wouldn't even know, or at least we wouldn't agree, that the sun revolves around the Earth. So there are a lot of important implications to what Brahe did, even though he was really just this crazy guy writing stuff down. He tried to be a scientist. He wasn't very good with physics, and he kept making up laws that weren't true. But Kepler was very smart at using the data. It's the partnership between these two that made modern astrophysics and astronomy possible. So why is this relevant? It's probably going to be a stretch. I just thought it's kind of a fun story to tell. But this is what we do at Keen.io. So we've built an observatory. What we do is we make technology that allows software developers who are making any kind of software, whether it's in an embedded device or whether it's in a mobile game or a social networking website or in an automobile. We allowed those people making connected software to record history in a very precise level of detail at a very, very large scale. And then we allow them to analyze that data on our infrastructure. So we're basically Brahe in the story. Our customers are Kepler. We're not geniuses. We just know how to make this thing that can collect stuff really well and open it up. And what we're seeing now is we're seeing our customers are starting to detect the same pattern, and they're opening up their data using our platform to their own customers and partners. So that's a kind of brief history of kind of what we do, I guess. But I wanted to talk a little bit about, so we're a buzzword bingo kind of company, right? We're a cloud API platform for IoT, analytics, and big data. Like, what is that? That doesn't mean anything, right? So I'm going to talk a little bit about what those buzzwords mean to us and why we use those words. So first of all, platform. Everyone says platform all the time now. There used to be a distinction between platform and solution, so I'm going to shine some light on that. A solution is something where you know a problem, and then you design something to solve the problem. That's a solution. A platform is something you build when you don't even know the problem. You're designing for some vague and blurry set of future problems that might come up, hoping that other people will come be smarter than you, and that's what we hope we're going to find is people smarter than us to build solutions. So history is full of examples of this kind of perspective where, belief. So Brahe was recording data based on belief. Belief can sometimes be stronger than need, because lots of people wanted to figure out how the stuff in the sky moved around. They had need, and they were going from the need, trying to build a solution. Sometimes it requires a partnership of people who can build a platform and people who can solve problems working together. So when we say platform, that's kind of what we mean. It's the basis for other people to be smarter than we are and build solutions. So IoT, this wasn't a word that I had heard 5 years ago. I've been in this business a long time. It turns out, I'm sure Forrester and Gartner and maybe some savvy futurists here had heard of it, but it's always been a little confusing to me because from our perspective as humans, we look at it like, oh, there's a thing and it's not on the internet. Once it gets on the internet, now it's Internet of Things. But I like to look at it from the internet's perspective, because that's like, I always say my hometown is the internet. I grew up online mostly. From the internet's perspective, let's say I'm the internet, and I don't know life before me. I've always been the internet. And suddenly there are some web servers and web browsers popping up on the internet. And it's like, okay, cool, there's a couple things on the internet now. And then mobile devices pop up on the internet. Oh, there's a new thing on the internet. From the internet's perspective, it's always been the Internet of Things. It's just that it used to be, for 10, 20 years, maybe 15 years, the things were mostly web browsers. And then the things progressed to be mobile devices and smart devices. And sensors, mostly starting with smart meters, I think, popped up. But these are really just new clients that know how to use and consume the internet. They know how to use APIs to connect with the internet. I have a colleague who's giving a talk at ThingMonk next month, which I love the name of his talk. I wish I could have just stolen it, but it's his talk. It's called I Connect, Therefore I Am. And the subtitle is something like, before a thing gets on the internet, does it actually exist? And from the internet's perspective, obviously the answer is no. So when I talk about IoT in enterprise, especially in sort of the global 2000 enterprise world, sometimes I'm a little thrown off because we all understand the power of IoT and how all these different ways that it has already changed things and it's going to continue to change things. But right now it's usually in silos, right? Like, I kind of think people are interpreting it as if we mean intranet of things, right? Like, I've got my IoT stuff, you've got your IoT stuff. Maybe we'll form a partnership and we'll ink something and we'll have some need and that'll drive us to allow access to our data. But I think that that's going to limit us in the future. I think that it's better to say, I don't actually know why we're going to work together on this stuff. I don't have an actual reason. I don't have a prescription for why I'm going to open up my data to my customers, my partners, to my users. But I'm just going to do it anyway, and then they'll surprise me. So I'm pretty much here to just implore you to think about the world. Think about the reasons why you're locking your data in, because I think most of it's corporate habits from before we even had the internet, right? We have IT teams who are used to locking the data in. They've existed since before the internet, so the culture and the inertia in our organizations is leading us to, hold tightly our data. But I mean, I've built an entire company on the notion of opening it up. Open public APIs, public cloud only. That's the only way that our platform works. And we give discounts to people who share their API keys with the public. And we're starting an initiative to bring all of the open government data online, completely free to use. Not because we think, well, maybe there's some strategy to it, maybe we think it's going to help with our branding or something, but really what it comes down to is we want to do like Brahi did and allow other people to use the data to find things that we didn't know, and our customers didn't know, and their customers didn't know maybe they could be used for. So yeah, I'm San Francisco hippie, sharing and openness all the way. That's me.
Let's thank our speakers. And now I want to open it up to you all. We're open to questions. Go ahead. Is there a microphone? Oh, you have a microphone. Okay. Over there. Over here.
I'm sorry, could you raise it?
Oh, the question is, the first question, obviously I will ask more later when I get more chance. The first question is, all these sensors, at this moment, we don't have a well agreed upon standard for all the sensor devices to use it as a common network protocol. For example, like you take your smartphone out, there are 3 interfaces, very well defined: Bluetooth, cellular infrastructure, and Wi-Fi, right? But most of sensors, I mean, what kind of a interface have they been using? It's been debating all over the world. So what is the Fujitsu's view in that world? Because you have shown the data saying that, okay, demand response. For all we know, demand response using the traditional internet, I mean, layer 7 protocol to get things across. But what about the sensor world? I mean, all these sensors, a lot of them are constrained, resource-constrained devices. I mean, they cannot afford to run Wi-Fi, for example, right? I mean, so what is the protocol you folks have already endorsed? I'd like to have a better understanding on that. Of course, I mean, other questions I'll ask later.
So this is a very good question, and maybe I'll start addressing it since you mentioned demand response. Standards are always a challenge, and a lot of times it's not that we don't have a standard, it's that there are several, at least 2, sometimes more than 2, but they essentially fragment the market. In the energy space, we're lucky that a lot of our devices are powered. For example, a smart meter is connected to the power grid, so it has a wireless interface. Some of them even have Wi-Fi interfaces. Some of the other devices, like thermostats, are also powered. That we can use to, for example, during demand response events. And in the least, in different layers of the networking layer, there are multiple standards, but in terms of home automation that plays into demand response, there are currently two, 802.11 based and 802.15 based standards, and they're still fighting it out a little bit, so it depends on whether you believe Wi-Fi will win or Zigbee based standards will win. So, sorry? Go. I'm sorry?
There's another one called Thread.
Thread?
That's also 802.15.
Yeah, so 802.15 has a number of different substandards as well. But in terms of what devices are already out in the market, we're seeing a lot of Wi-Fi, to be honest. But we'll see. Will Wi-Fi take over the world or not? I don't know. And I want to let if anybody else wants to comment on this question.
Sure, I'll jump in with some thoughts on the personal sensor side, because there the sensors are not powered, and so battery becomes the biggest constraint. So at least in the current generation of market sensors, we see Bluetooth Low Energy being the overwhelming choice of vendors who are shipping products this year or even last year. And that's primarily because of battery technology constraints. The other thing is that, we sort of, for example, in the work that we did at the lab, we started when the sensors were wired. And so we actually made a hardware prototype instead of a software prototype, because the smartphones at the time were not open enough to get data from these things. But to solve that problem, we made a little mobile hub, which was capable enough to talk to the sensors using the protocols they spoke at the time. And now, the smartphone industry, recognizing their place and privilege as the hub of this data, mobile data, is building in that hardware to talk to the protocols of the day, of the year, of the 5-year period. And I think that will evolve. As the protocols evolve, the hubs will continue to be capable of talking to them. And finally, I would say that at a more higher level, the multiplicity of protocols does not bother me personally, because I think it just shows that there is a lot of innovation and continuous striving to improve the current protocols, either on energy efficiency or data throughput rates. There's always going to be a receiver on the other end of the protocol, and given that it's the Internet of Things, where at the physical layer you're going to support multiple communication and physical layer protocols, at the abstraction level above it in software, those things, especially with open APIs and platforms, will not be a constraint for developers to build services that change our businesses, change our lives. And so that's why it doesn't worry me. I think it's, the industry is aligned to make the system work well together, even as it evolves. So those are some thoughts.
I will add, I don't know if this is working, that there's an old joke from the HTTP world. It maybe is older than that, but I'm not. So the joke is, somebody looks at the world and says, oh, we have N standards, we really should just have one. And now you have N+1 standards. Yeah. But I think it runs to the heart of it. It speaks to the point that I think that there's a balance, a tension of incentives here. There's the humanist perspective that says we should have a standard. There's the corporate perspective that says our company should own the standard. And the proliferation is always going to happen. I think things will eventually consolidate if they need to. So it doesn't worry me either.
Yeah. As for the standards, interoperability is a big, important problem. So there will be many standards, but we need to talk to each other. So, for example, Wi-Fi and LTE is maybe in the future will be migrated. So we don't care about the Wi-Fi connection or long-term evolution connection. So interoperability is a big problem, and is important. And as for the energy, yes, small sensors need a battery. The battery is the problem. So Fujitsu Laboratory is doing the research of the energy harvesting, like the body heat. You can generate the electricity. So using that kind of electricity, you can use the small sensor, sending the data to the mobile phone. So from that kind of research activity is already going on in the Fujitsu Laboratories. I'm sorry, I didn't bring the prototype over there, but you can check in the internet.
Yes, looking forward, we still have a little bit more of time with Moore's Law. And you're being able to do analytics in many different places other than a centralized cloud infrastructure. And I'm wondering any take on how you see using distributed analytics.
So I can briefly comment on that. I think in every distributed system, you have to make a choice where to process the data, how to trade off communication versus processing and storage. Ultimately, for better efficiency, we do need to have localized processing to the extent possible rather than moving large quantities of data unnecessarily back and forth. So I do see some processing happening at the end to at least aggregate some of the information rather than sending all the data back to a centralized location where it gets processed there.
We have now the data center and devices, but in the future, edge computing or edge analysis will be necessary because of the restriction of the network bandwidth, and we also need a real-time processing because the data is very huge. So it is very difficult to gather all the data to the one data center. So we need edge computing or edge analysis in the future.
I agree with that. I would add that. So one of the things we talk a lot about at Keen.io is this question is about the 3 dimensions. Where is the data physically, and where's the processing happen? We think a lot about the 4th dimension, which is when does the processing happen? And so a good example is like the way our technology works. We expect data to be formatted in a very denormalized way, which means every time somebody, let's say you're doing clickstream analytics on our platform, every time somebody clicks an ad, you actually will send us an entire browser and user object with that click event, which violates tons of principles from computer science around normalization and redundancy. But what it gets us is a little bit of extra work inside of, let's say, an Android device or a web browser to make that data more analyzable, and then we can analyze, we believe, trillions of events in under 5 seconds because they've been formatted appropriately. So that's a question of when, right? Like you can do some edge computing beforehand that makes things more efficient too.
Jorjeta, we've run out of time, I'm afraid.
Oh, we're getting shut down.
You're going to be shut down. Thank you so much, everyone, for attending, and thank you, panelists. Thank you, moderator. We really appreciate it.